Good day. This is a project by myself, Khair Ali, my colleagues Haifeng Mei, Aaron Suku, and Cyan Chang. We are the group Intelligent Solutions Inviting Success. Please note that we are unaffiliated with any organizations bearing the same acronym. We are here to discuss challenges facing UWI's internal transport network. UWI shuttle service is unreliable. There have been numerous complaints about long wait times. Students are uncertain whether they should wait for a shuttle or if it would be faster to walk to their destination. There is a schedule for shuttle service, but in practice, shuttles are often delayed and vehicles are sometimes off duty. In these cases, the drivers left need to service multiple routes in different directions, sometimes on the same trip. Adding to all these frustrations is the lack of current information about the shuttles and their locations. Every modern transport hub, like an airport or train station, has some form of information about vehicles and ETA. The existing shuttle system offers no such amenity. We have a solution to these problems, a new system that completely overhauls the shuttle service and will provide far more flexibility and convenience. This solution is based on a set of requirements influenced by modern transportation schemes, supplemented by real-time information systems. To interact with the system, users can authenticate with their existing ID cards, or as an alternative, an authorized profile can be installed to their smartphone. After authentication, passengers can select a destination from a preset list. For after-hours operation and safety reasons, passengers would be able to specify a custom destination, their nearby home or apartment, for example. The shuttle ETA will then be updated and displayed to them. Drivers are required to authenticate as well. Only then will they be allowed to operate a vehicle registered with the system. At any point, the authenticated driver can change the shuttle status. The system will display route information to the driver. System administrators will be able to modify asset data. They can add or remove drivers, vehicles, and stations as conditions change. The system itself should be able to calculate the ETA of a shuttle to any station along its route each minute. It will calculate the best route available based on real-time conditions. The system will be able to track people inside a shuttle as well. It will determine which shuttle a passenger should board within 5 seconds of the passenger's request. It should then verify the boarding activity of each person and keep a real-time count of vehicle occupancy. To maintain security and help prevent abuse, the system will require access to UWI's personal database, simply for verification and authentication.
Now we look at how users interact with the system using use cases. Each use case represents a task the user of the system can perform. There are two main actors involved, student and driver. Students are able to check in at the station and the shuttle. Drivers are able to log in and log out, change the shuttle status, and select a custom destination. These use cases reflect the requirement that was mentioned previously in the overview. First, we can look at the primary task in the form of an extended use case. Students can check in at the station by the following steps. They scan their UWI ID card or QR code as input. If invalid, they will be advised to seek external assistance. If successful, they are greeted by the destination selection screen. They will pick where they wish to go and the system will designate a seat for them within a particular shuttle. The ETA will be calculated and displayed. If a student accepts the wait time, they can confirm the seat assignment and wait for the shuttle's arrival. Students can look at the ETA monitor that is placed at every shuttle tub, or they can look at the respective mobile app to track each shuttle's ETA. When the shuttle arrives, we proceed with the next extended use case. Students will now board the shuttle by checking in. In order to verify that each student board the designated shuttle, they are expected to validate themselves using their UWI ID or mobile device. The driver will be able to see the confirmation or denial message on his system monitor. Boarding data will be recorded for statistic analysis to improve efficiency of the system. The system may reassign empty seat as appropriate to waiting student in queue. The student will disembark the shuttle when they reach their respective destination. Other use cases involve the driver interacting with the system on the shuttle itself. In order to operate the shuttle, the driver must first log in via ID card validation. Once he's logged in, the system will register him as an active driver of a particular shuttle. While operating the shuttle, he can change the shuttle status from offline, en route, standby, or waiting. He also has the option to select a custom destination for night hours to safely drop passengers home, or he can change destination in response to unexpected circumstances such as a car accident. This concludes the main interaction between user and the system.
The first sequence that we will look at is the occurrence of verifying with the system. The student requests a check-in by using his student ID. The system takes this ID and sends it to UE's personal authentication. If this is returned as false, the Smart Shuttle system will trigger its lock subroutine and return a failed authentication message. If the verification status is true, then it will continue. It will send the list of destinations to the student, who can then pick out a destination referenced by its destination ID and pass it back to the Smart Shuttle system. The system will then assign a shuttle using the student ID and the destination ID and return the information about the shuttle the student needs to board. The student must now wait for a vehicle to arrive. In order to board a vehicle, they need to use their ID or smartphone once more to check in at a terminal on the vehicle itself. If they attempt to board the wrong vehicle, the Verify Student ID subroutine will return an entry denied message indicating that this is the wrong shuttle. For the correct shuttle, there will be a positive feedback, entry granted. The system itself now will update the seat occupancy for that shuttle, and it will trigger the statistics gathering routine that will keep cumulative counts of number of students, the destinations, the time, general pattern analysis statistics, and generate a report for the system. There is a scenario in a case where a student may request a shuttle and then fail to board it. In this case, the system will trigger a routine to reassign a reserved seat. If there are other students waiting on other shuttles, but they could be accommodated by this one, which now has an unoccupied space, the system will update the information and allow additional students to board to increase its efficiency. The strength of this system lies in its ability to handle the information it gathers. This information needs to be represented in an organized manner. The way we have come up with is as follows. Each person is represented as a user. They would already have a UE ID number. This ID number is stored along with their name as a general user class. The user class is extended by the student and driver subclasses. The student has methods to request check-in to the station and to request entry to the vehicle itself. The driver has methods sign in for when he starts work for the day and sign out for when he finishes. Each vehicle in the fleet is also registered with the system using their unique license plate number. The vehicle class also contains information like the number of seats and the vehicle make and model. When a driver is assigned to a vehicle, it is represented as a new class called Shuttle. Here we have the Shuttle ID. It uses the driver ID and the license plate number, as well as a new count called available seats. It also has a shuttle status, which the driver can change, and the method change status. Each station is represented in the destination class by a unique ID, its name, and its physical coordinates. In order to dispatch a shuttle, the student activates the request check-in method. It creates a new check-in event. This check-in requires a destination endpoint. It uses the pick destination method at the station terminal. A shuttle is then dispatched for that particular check-in and any other appropriate check-ins that can be applied to the route. Upon entering a vehicle, the student's request entry method triggers a boarding event. This is represented as a new class and keeps track of each student boarding any given shuttle at any time, any day. The boarding event and the check-in for any given occurrence are linked together by a class called Trip. This is representative of the check-in from the station, followed by the boarding and eventual disembarkation of a student from a vehicle.
The cost model and technique used to estimate costs for this project are constructive cost model, COCOMO, and estimation by analogy, as it was decided that these methods would allow for an accurate estimation of costs. COCOMO was used to estimate the software costs. To use this method, the size of the software needed to be estimated. Estimation by analogy was used as similar projects have been undertaken, which allowed for comparisons between those projects and this one to determine the other costs. The COCOMO uses the attributes seen on the slide and gives them a rating that ranges from very low to extra high. The intermediate COCOMO formula was used, which multiplies the value received by the cost per point of $1,000 to arrive at the value of $25,920. When combined with the cost of salaries, hardware, and maintenance, the total cost of the project is estimated to be at $93,450. This cost can be justified because a new system is definitely needed, as the current system is unreliable, inefficient, and unpredictable. Also, UB has a fairly large student body of approximately 20,000 students. The cost of this project can be easily covered by using the amenity fees of only 187 of those students.
The next phase of the project is testing. This is done in 3 stages. Firstly, we performed unit testing. To do this, we check to see that the user is able to change the shuttle status and select a destination. We also check that the UE ID cards were the only smart cards being accepted by the system. We verified that updating the database required a particular format of data and that the QR code generated by the application is readable by the system. Each of these tests were done separately and 15 times each. The functions passed each time. Next, we performed acceptance testing based on the requirements described earlier in the project. Essentially, this is component testing done to ensure the accurate flow of data. The acceptance tests performed were authentication of a UE ID card, calculation of a ETA, assigning a shuttle to a student, calculating the best route, and displaying the ETA of a shuttle assigned to a student. Each of these tests were done separately and 15 times each. All passed except calculating the ETA failed on the 3rd test. Lastly, system test was performed based on the user cases described earlier in the project. These included check-in station, check-in shuttle, logging in of the shuttle driver, adding a custom destination, and changing a shuttle status. Every system test was done 15 times and all passed, except checking at the station failed after the 5th iteration. For the failed acceptance and system test, changes were made and each were retested 15 times and passed.
Several risks will be involved in the undertaking of this project. These risks range from major risks that will have severe impact if they were to occur to minor risks that can be tolerated. The major technology risk is if the system cannot process as many transactions as possible. Although the probability of this risk occurring is low, it will have serious effects on the product if it were to happen. The strategy put in place is a contingent one and will involve investigating the possibility of obtaining a higher performance system within the budget. A major organizational risk that can occur is if the organizational financial problems force reductions in the project budget within the duration of the production. The probability of this risk occurring is moderate, and if it were to occur, it would have catastrophic effects that will affect both the business and the project. The strategy put in place to avoid this risk is by showing how important the project is and reasons why cuts to the budget would not be cost effective. The major requirement risk that can occur is if the requirements of the product change. The probability of this risk occurring is moderate, and if it were to occur, it would have serious effects that will affect the project, and business. The strategy put in place is one to minimize the effects of the risk by drawing up a contract stating if requirements changes are allowed, how many changes are allowed, and the consequences of these risk changes. Finally, there are 3 major estimation risks that can occur. If the time taken to develop the software is underestimated, then it can seriously affect the project. To avoid this risk, a project manager can be hired to assist in the planning phase of the project. If the time taken to deliver and install the system is underestimated, then it can seriously affect both the project and the product. However, this risk can be avoided by buying in components. The final requirement risk that can occur is if resource requirements such as processing power of hardware components are underestimated. The probability of this risk is low, but it will have serious effects on the product if it occurs. This risk can be avoided by investing in reputable, high-performance components. There are also several minor risks that can occur, however, these risks can be tolerated. These risks are: if the project has an unrealistic scope, time, and cost objectives with respect to the organization's resource or structure. The probability of this risk occurring is low and it can be avoided by possibly hiring a project manager to assist in the planning phase of the project. If people decide to leave the project, this will affect the project, product, and business as well, but will have a very low chance of occurring. It can be avoided if the leader of the project can enhance the morale of the other employees and develop a good relationship with the team members. And if it were to occur, we can ensure that there is an overlap in work so someone else can take over the job of the person leaving. The last risk is if the key staff are unavailable at critical times. The chance of this risk occurring is moderate as people are fickle and cannot predict any unforeseen circumstances that may cause them to be unavailable, but if there is overlap in the flow of tasks, then everyone understands each other's jobs, so it will not have a big effect.